Our last video ended with asking you to fill out the truth table for these 4 different conditional statements. And we've started the setup for that right here, so I'd like to begin this video by going over the answers. Filling in the truth table for P implies Q is just as simple as going back to the truth table we had seen before and filling in the values. We notice that much like an OR statement, a conditional statement only has one false value, and that occurs precisely when the antecedent is true and the consequent is false. So we have true, false, true, true right here. Looking at Q implies P, the only location of the false inside this conditional statement will be when Q is true, so either here or here, and P, the consequent in this situation, is false. So that's right here in the 3rd row of the truth table, and we see that this truth table should read true, true, false, true. Notice right away how P implies Q and Q implies P are not logically equivalent. They happen to be the same in the situation where both P and Q are true, or when P and Q are false. They both have true values there. However, the switching around of the true and the false values in the middle 2 rows changes the truth tables. And so these 2 statements, P implies Q and Q implies P, are not logically equivalent. Moving on to not P implies not Q. If we were working with pencil and paper, I'd probably want to add columns to this truth table for the negation of P and the negation of Q. But let's see if we can locate that one false value. Our false value will occur when not P, the antecedent in this implication, is true. So it will have to be one of these 2 rows. And not Q will need to be false. Q is true in the 3rd line, so not Q would be false in the 3rd line. So in this 3rd line, not P would be true, not Q would be false. The false should go right here, and the rest of our values should be true. So these 2 statements, Q implies P and not P implies not Q, are in fact logically equivalent. They have the same values in every row of the truth table. Again, this conditional statement, the inverse, is not logically equivalent to P implies Q because of the discrepancies in the 2nd and 3rd row. Last but not least, let's look at the contrapositive, which is of the form not Q implies not P, and let's determine where that false value goes. Not Q will need to be true, so we'll be in either row 2 or 4, where our false value will be, and not P will need to be false, which happens in rows 1 or 2. The overlap of those 2 situations is row 2, so checking row 2, not Q will be true, not P will be false. This is the row where our false will go and everything else will be true. So we see here that P implies Q, our original implication, is logically equivalent to its contrapositive. It is not logically equivalent to its inverse or its converse. However, those 2 statements are logically equivalent to one another. So to summarize that, I've got a lovely visual. On the one hand, we have P implies Q and not Q implies not P being logically equivalent and the same exact statement or picture. On the other hand, we have Q implies P along with not P implies not Q. Those 2 things are the same as one another, but if we were to have an ultimate like mega meme, the picture over here on the left is not the same as the picture over here on the right. The last thing that I really want us to do with implications and logical equivalence is realize that in fact this symbol of implication is superfluous. It's really good at characterizing the way we come across logical statements in the real world. However, it's very frequently much more useful from a propositional logic standpoint to replace this conditional statement P implies Q with something that is logically equivalent to it that only uses our original logical operators and, or, and exclusive or, along with our negation. So in order to figure out what that is that might be logically equivalent to P implies Q, I again want us to look at the truth table. As mentioned previously, our implication only takes on one false value. And when I think back to the truth tables for ands, ors, and exclusive ors, the number of falses that occurred in those truth tables was unique. There were 3 false values that occurred in the and truth table, 2 false values that occurred in the exclusive or truth table, and 1 false value that occurred in the or truth table. So if I were to guess what P implies Q is logically equivalent to, I would think that the ultimate statement would need to involve an or somehow. However, it's clear that P implies Q is not logically equivalent to P or Q. That does have a single false value in its truth table, but that false value in the regular or statement P or Q would occur in the 4th row, not the 2nd row. So what we would need to have an or statement with a false in the 2nd row is 2 false values occurring there. Q already happens to be false, but P in this situation is already true. So what if we looked at not P? If we add in a helper column for not P and combine not P with Q via our or statement, in the 1st row we have a true and a false, so we'd put a true here. In the 2nd row we'd have a false and a false, so we would put a false here. And in the remaining 2 rows we have at least 1 true, so we'd place a true here and a true here. This shows us that the implication P implies Q is logically equivalent to the statement not P or Q, which goes back to the idea of our original example and the rules. Remember the rule that anything follows from a false antecedent. In other words, either it's the case that the antecedent is false, in which case everything will be true, or it must be the case that we're following the rule. We do have the antecedent and we do follow the rule. So it's very important to know that our conditional statement P implies Q is logically equivalent to this column over here on the right, not P or Q. The reason it's so important for us to remember this is that it turns out to be very helpful for working with how to negate an implication. And because implications are everywhere in our world and can be often used in deductive reasoning, it's really important to think about what kinds of conclusions we can draw in the event that an implication turns out to be false. If we have a chain of events and that first domino does not fall over, what else is out of line because that first domino does not fall over? So this is a really useful life skill. And so I'd like to end this video with another exercise. So all I've done here is I've included the truth table from the previous slide with values for P, Q, our implication, and something that's logically equivalent to our implication. And I've added one more column, which is the negation of the previous column, where all I've done is taken the trues and turned them to falses, and the falses and turned them to true. What I'd like you to think about for an exercise is how many false values appear in this column. What does that seem similar to in terms of our previously understood logical operators? Does it seem most similar to an and statement, an or statement, or an exclusive or statement? And can you come up with some combination of P's, Q's, nots, ands, ors, and exclusive ors that's a simpler way to write down the negation of P or Q? That's the exercise I'm going to leave you with, and we'll talk about that perhaps in person.